Good morning, guys. Today we will discuss or we will solve the numericals which is based on the temperature effect, means one-dimensional bar system with temperature effect. Okay, in previous lecture actually we have solved one example. Now in this lecture also we will try to solve this example. Okay, this example actually is asked for 12 marks in your end semester examination. This example is asked for 12 marks. Okay, so all data it is given except in the example, as there are three elements or there are three bars which is made up of steel, brass and aluminum. Okay, left and right end, both ends are fixed, and also all the input data it is given here itself. So area, Young's modulus and coefficient of thermal expansion for this first element is given. Likewise for second and third element also the area, Young's modulus and coefficient of thermal expansion is given. Okay, so in this example here they are asked to find out the nodal displacements at node 2 and at node 3. Okay, similarly the point load is acting at node 2 and at node 3, and the value of point load P1 and P2 is also given. P1 is equal to 49 kN and P2 is equal to 20 kN. Okay. Similarly, lengths of these three elements are given. For first element length is 1000 mm, for second element it is 80 mm, it is 100. It is actually 100 mm. For second element it is 80 mm and for third element it is 60 mm. Okay, so here it is asked to find out the nodal displacements at node 2 and at node 3. Then find out the stresses in each element. Means we need to find out sigma 1, sigma 2 and sigma 3, and the support reactions at node 1 and at node 4. Okay. So this is asked for 12 marks in your end semester examination. Means first bit it is asked for 4 marks, second it will be asked for 4 marks, and third one it is asked for 4 marks. Okay. So in this way 12 marks are distributed. So now we will try to solve this example right now. So our first step is what? First step is to construct the global stiffness matrix. For this we need to find out the elemental stiffness matrices for each element. For element 1, 2 and 3. So we need to find out the elemental stiffness matrices K1, K2 and K3 for each element. So K1, so elemental stiffness matrix for the bar system, it is, we know that it can be written as AE by L, is A1 E1 by L1 in bracket 1 minus 1 minus 1 1. Okay, so A1 E1 and L1 all the values are given. A1 is nothing but 1000 mm square, E1 is equal to 210 gigapascal. So we need to convert this in megapascal. Why? Because we need to convert all the units in mm square or mm, Newton per mm square. So if we convert this to 10 gigapascal into Newton per mm square, it will become equal to 210 into 10 raised to power 3 Newton per mm square. Okay, so 210 into 10 raised to power 3 into A1. A1 is equal to 1000 mm square divided by L1. L1 is 100 itself. It is equal to 100 into 1 minus 1 minus 1. Okay, so on simplifying this we will get 21 into 10 raised to power 5. 1 minus 1 minus 1. So in this way you will get your first elemental stiffness matrix as K1 is equal to 10 raised to power 5. 10 raised to power 5 it is common. 10 raised to power 5 into 21 minus 21 minus 21 20. Okay. Similarly second elemental stiffness matrix. Okay, this is second elemental stiffness matrix. So for this the values are A2, A2, L2. So it will become equal to, here A2 is equal to 500 mm. 500 into E2 is given as 100 gigapascal. So we need to convert it to Newton per mm square. So it will become equal to 100 into 10 raised to power 3. 100 into 10 raised to power 3 Newton per mm square divided by L2. L2 is equal to 80. 80. So on simplifying into 1 minus 1 minus 1. Okay. So on simplifying this, we will get 0, 0, 50 into 10 raised to power 5 divided by 8. So 6.25 into 10 raised to power 5 in bracket 1 minus 1 minus 1. Okay. So finally you will get K2 as 10 raised to power 5 into 6.25 minus 6.25 minus 6.25 and 6.25. As we know that the position of first element is in between node 1 and 2. Its position is between node 2 and node 2. Then finally K3 elementary stiffness matrix for third element. K3 is equal to A3 E3 by L3 into 1 minus 1 minus 1. So you will get A3 is equal to 300 into A3 is equal to 75 gigapascal. So 75 into 10 raised to power 3 Newton per mm divided by 60 into 1 minus 1 minus 1 1. So you will get 5 into 75. So 5 into 75 into 10 raised to power 3. So actually we need to convert this into 10 raised to power 5 also, because 10 raised to power we have taken 10 raised to power as a common. So 5 into 75 it will become 375 into 10 raised to power 3. It means 3.75 into 10 raised to power 5 1 minus 1 minus 1 1. So finally K3 will become equal to 10 raised to power 5 in bracket 3.75 minus 3.75 minus 3.75 3.7. Okay. In this way you will get K3 also. Now we need to construct our global stiffness matrix. The position of this matrix, it is in between node 1, 2, 3, 4, between 3 and 4. Between 3 and 4. Between 3 and 4. As we know that this is your first node, second node, third node and fourth. Okay. So in this way your global stiffness matrix or order of your global stiffness matrix is equal to 4, because there are 4 nodes, so it should be of 4 by 4. So we will construct now global stiffness matrix. K is equal to, now this 10 raised to power 5 it is common to all elementary stiffness matrices. So taking 10 raised to power 5 as a common, 1, 2, 3 and so write down elementary stiffness matrices for the positions between 1 and 2. 21 is there. Between 2 and 3, 6.25 is there. Plus 6.25 minus 6.25 minus 6.25, 6.25. Between 3 and 4, 3.75 is there. So plus 3.75 minus 3.75 minus 3.75 and 3.75. Remaining elements equal to 0. 0, 0, 0. So 10 raised to power 5 into this global stiffness matrix. So in this way you will get global stiffness matrix as, here in this example this temperature rise of 60 degrees Celsius is also given. 60 degrees Celsius of temperature rise is given. So finally your global stiffness matrix K will become equal to 10 raised to power 5 into 21 minus 21 0 0, 21 minus 21 0 0, minus 21, now 21 plus 6.25, so 27.25, so minus 21, 21 plus 6 means 27, 27.25. 25, then minus 6.25, 0. Okay. Then 0 minus 6.25, 0 minus 6.25, 6.25 plus 3.75, 6 plus 3, 9, and plus this one, 10. And 0. Sorry, minus 3.75. Minus 3.75, 0, 0, minus 3.75 and plus 3.70. So in this way, you can write your global stiffness matrix. So global stiffness matrix will become K is equal to 10 raised to the power 5 into this matrix. Okay, so in this way you will get the global stiffness matrix. Okay, now next step is what? Next step is what? As the temperature rise of 60 degrees Celsius is given. It means we need to find out the global force vector due to this temperature effect as well as due to the point. So first we need to find out the nodal force vector. First we need to find out nodal force vector due to temperature rise of 60 degree Celsius. Okay, so first we need to find out the nodal force vector due to temperature rise of 60 degree Celsius. So for this we know the formula. So for first element, it will become F1T, F2, because this element is actually, it lies in between node 1 and node 2, so it will become F1T, F2T is equal to minus E1, A1, alpha 1, delta T plus E1, A1, alpha 2, delta T. Okay, in this way you will get the first nodal force vector due to temperature rise for first element. So on putting all these values of E1, A1, alpha 1, delta T, you will get F1T and F2T values as, so these values are equal to first one F1T, F2T, it is equal to minus 1,51,200 and plus 1,51,200. Okay. Similarly, for second element, for this element, this will become this for second element. For second element, it will become between node 2 and 3, F2T, Ft. The same process, minus E2, A2, alpha 2, delta T plus E2, A2, alpha 2, delta T. So it will become equal to, second value is equal to 60,000 minus 60,000 plus 60,000. Okay. Similarly, we need to find out for third element. Okay. So for third element it will become between node 3, F3T and F4T. So it will become equal to, if we write down this formula as minus E3, A3, alpha 3 delta 3 plus E3, A3, alpha 3 delta 3 delta T is equal to, on simplifying all, by putting all these values into this equation or into this formula, you will get third value as, third one is minus 32,400 plus 32,400. Okay, so in this way you will get the third nodal force vector due to temperature rise of 60 degrees Celsius. Okay, so for first element, this is the value. For second element, between node 2 and 3, F2t and F3t, this is the value. And for third element, F3t and F4t, this is the value. Now, we need to construct the global force vector due to temperature rise only. Here, these are the elemental force vectors due to temperature rise. We need to construct it to get the nodal force vector due to temperature rise. So for this, we know that. Okay, so how to construct means by simply adding these three nodal forces, you will get the nodal force vector due to temperature rise. Okay, so nodal force vector due to temperature rise is written as F1t, F2t, F3t, F4. So we can write this as, so for first element F1t, F2t, it is equal to minus 1,51,200 plus 1,51,200. So write down this minus 1,51,200 plus 1,51,200. Okay, next for second and third, between second and third node we have minus 60,000 plus 60,000. Between second and third we have minus 60,000 plus 60,000. Okay, between second and third node. Now between third and fourth node we have minus 32,400 plus 32,400. So between third and fourth we have minus 32,400 plus 32,400. So in this way you can construct your global force vector due to temperature rise. Okay, so on simplifying all these values, we will get the nodal force vector due to temperature rise as, so on simplifying, we will get the nodal force vector due to temperature rise as, so F1t, F1t, F2t, F3t, F4 is equal to, first one is minus 1,51,200. Second one is 1,51,200 minus 60,000. So it will become equal to 1,51,200 minus 60,000. It will become equal to 91,200. Okay, 1,51,200 minus 60,000 is equal to 91,200. Third one is 60,000 minus 32,400 is equal to 27,600. And third one is 32,400. So in this way, you will get this nodal force vector due to the temperature. Okay. This is the nodal force vector. Nodal force vector due to temperature. Now we need to find out the nodal force vector due to point P. Now nodal force vector due to point P. So this is given as F1P, F2P, F3P, F4P. So it is nothing but for first node there must be some reaction. So point load is equal to your R. For second node this P1 is given. Now P1 is equal to 49 kilonewton is given. So P1 is equal to 49,000 newtons. For third node, this P2 is given, but this P2 it is acting in opposite direction. Okay, so this will become equal to 20 kilonewton. 20 kilonewton means actually it is acting in opposite direction, so we need to take it as a minus 20,000 newton. And for this fourth node, there must be some reaction, so it is equal to R. Okay, so in this way you will get the nodal force vector due to point. Now next is what? Find out the global force vector due to temperature rise as well as point. So by simply adding these two force vectors, you will get the global force vector due to temperature rise as well as point. So here, if we add these two values here only, okay, you will get the global force vector. F1, F2, F1, F2, F3 and F4. So by adding these two, this is due to temperature rise and this is due to point. Okay, so finally you will get this F1 and F2 as, so on by simply we add, so this will become R1 minus 1,51,200. This will become R1 minus 1,51,200. 91,200 plus 49,200. So 91 plus 49. This will become finally equal to 1,40,200. This will become 1,40,200. 27,600 minus 20,000. It will become 7,600. 32,400 plus R4 means it will become R4 plus 32,400. R4 plus 32,400. Okay, so in this way you will get the final global force vector due to temperature as well as due to point. Okay. So next step is what? Now we need to construct, as we have already constructed our global stiffness matrix. Then here we have constructed our global force vector due to temperature rise as well as due to point. So we need to construct now this force vector and displacement vector relationship. Okay. So this force is nothing but this value. Is equal to K is nothing but your this global stiffness matrix 10 raised to the power 5 in bracket 21 minus 21 0 0 minus 21 27.25 minus 6.25 0. Third one is 0 minus 6.25 10 minus 3.75 0 0 minus 3.75 and 3.75 into displacement vector. Displacement vector is what? U1, U2, U3, U. This is our displacement. So in this way we have constructed our force and displacement relationship. Now next step is what? Apply the boundary conditions. So boundary conditions for displacements are, so as we know that first node is fixed node. So at this node displacement or there will not be any movement. So displacement U1 is equal to 0 for this first node. And for the last node, this node is also fixed one. So U4 is equal to 0. So as we know that these two values are 0, so we need to eliminate this first row, first column as well as fourth row, fourth column. Okay, so eliminate first row, first column, fourth row, fourth column. So here we will get only these two equations will be remaining here only. Two equations will be remaining. So write down these two equations. 1,40,200 is equal to and 7,600 is equal to 10 raised to the power 5. 10 raised to the power 5 into 27.25. 27.25 times u. 27.25 times u minus 6.25 times u minus 6.25 times u. Similarly, for this 7,600 is equal to 10 raised to the power 5 into minus 65 minus 6.25 times u2 plus 10 times u plus 10 times u. So in this way you will get these two equations. Okay. So on solving these two equations, 10 raised to the power 5 we get cancel it. So it will become 1.40. If we cancel it here, 0.0760. So by solving these two equations now, you will get u2 and u3. So by solving these two equations, you will get u2 as solve these two equations, you will cancel it. You will get u2 as, so the value of u2 is equal to 0.06. So u2 is equal to 0.06636 mm and u3 is equal to 0.067 and u3 is equal to 0.06769. So in this way you will get the displacement values. Okay, now next step is what? To find out the stresses. To find out the stresses, we know that the formula is sigma 1 is given by the formula E1 by L1 in bracket U2 minus U1 minus E1 alpha 1 delta. Okay. E by L, U2 minus U1 minus E alpha delta. E alpha delta. So in this way, if you put all the values here, you will get sigma 1. Similarly, sigma 2 is what? E2 by L2 in bracket U3 minus U minus E2 alpha 2 delta.